Hi, everyone. This week we are talking about rational functions. So this is going to extend the polynomial stuff from the last couple of weeks and show us kind of how we can, apply that to a little bit different situation. Now we've talked about combining functions before, like how you take two functions and add or subtract or multiply. And the thing is that with polynomials, if we take two polynomials like x plus 1 and I don't know, x squared plus 2x plus 3 and add or subtract or multiply them together, what we get is another polynomial, right? Think about multiplying this. You would distribute everything, and what you get is just a different polynomial. That changes a little bit if we talk about taking two polynomials and dividing, right? As usual, uh, division is a little bit more involved, a little bit trickier than the other operations, right? Division works a little bit differently. So because it works differently, it kind of gets its own thing and own set of stuff that go with it, and we call these rational functions. So the root here, rational, is the same as the word ratio. Rational numbers are fractions, right? Specifically integer fractions, but like 1/2, 2/3, etc., that kind of thing. Rational functions are fractions made of polynomials. So specifically, things where we have some polynomial in the denominator, so something still involving a variable in the denominator. I don't remember exactly what the thing I had just a second ago was. I don't know why I erased it, but something like that is an example of a rational function. This is a polynomial. This is also a polynomial. This is a fraction made of polynomials. So that's what rational functions are. We are going to spend several days kind of getting all of the ins and outs of how you work with these things, because they do have a bunch of kind of baggage that comes along with them. But to get a start on that, we're going to look at a sort of like a parent function. Like we saw with polynomials, they start to kind of vary a lot, right? They're not quite as distinct or as similar to the parent function as some of the stuff that we looked at earlier in the semester. But if I want a fraction made of polynomials and I want it to be different than stuff we've already talked about, a good straightforward example is what we sometimes call the reciprocal function 1 over x. So what this does is if you give it an x value like 3, it takes the reciprocal, which would become 1 over 3. This is a degree 0 polynomial. This is a degree 1 polynomial, so it does fit our standard, our definition for what a rational function is. But this is kind of about as simple as I can make it, that will show us all the stuff that happens, but be different than things that we already know. Here's its graph. We've seen graphs like this in a couple of places before, but we haven't really, done a deep dive on how they work. We're going to do that now. The first thing that probably jumps out at us is that this graph kind of comes in two separate pieces, right? It's in two separate branches, or if you want to think about sort of drawing it out, I can't draw the whole thing without needing to, lift my pencil at some point, right? The fact that it's in two pieces like that means that it is not continuous everywhere. A good working definition for continuity for us at this point is basically whether or not you can draw it as a single piece. This is in two pieces. I can't draw it as a single piece. So it's not continuous everywhere. Okay, well, we're talking about a function, so a good place to start is always by thinking about its domain. And what I see with the domain here is that all of these values are included, right? So appears to pass through any negative value that you want. All of these are included, so positive values. But the place where a weird thing happens is right here at x equals 0. As I approach x equals 0 from one side, the graph starts to turn very sharply and very steeply down in the direction of negative infinity. And on the other side, if I think about sort of moving, in towards 0, I get this end of the graph turning very sharply upward toward positive infinity. What that tells me, and if you want, you can graph this in Desmos and sort of zoom in and move it around, all day long. But what you're always going to see is a little gap. See how there's a little gap between the y-axis and the actual function? That gap's always going to be there, because if you think about trying to plug 0 into this, you get 1 divided by 0, which is undefined. What that tells me is that the domain is everything except 0. So I could write everything except 0 would be something like that. And I'll just make a note that that's everything except x equals 0. By doing open intervals on both sides, we're excluding the point 0 itself, but we can go as close to it as we want. This behavior that we see at the x-axis, the y-axis, at x equals 0. Basically, I can imagine a vertical line that would kind of squeeze in there and sort of fit into that gap where I sort of jump over from one piece of the graph to the other. Lines like that are called asymptotes. This one is vertical. It's at x equals 0. So anytime you get that kind of behavior where you can imagine a line sort of fitting in, it's not part of the graph, which is why I drew it in a different color, although maybe I can make it more different. There we go. It's not actually part of the graph, but it's sort of a feature of the graph in that it kind of gives me a like structure for what the thing does. It doesn't actually cross that line because as I get close to it, I have to sort of jump over, again, because I can't plug 0 into the function. But that asymptote then gives me kind of a good like guideline for drawing what the function actually does. So I'll just make a note here that this also has a vertical asymptote at x equals 0 because of that discontinuity. Right? Sorry, a discontinuity is a place where a thing stops being continuous. Right? So that place where we have to jump over it. Discontinuity. Okay. The other thing that we probably want to look at would be the range. So I do the same thing, but turn the graph or my head sideways and think about the y values. And if I think about y values, all through here I see the graph somewhere, all through here I see the graph somewhere, but it looks very similar, right? This one in particular looks pretty much the same from the side or upright. Y equals 0, the x-axis, appears to be a place where the graph doesn't actually pass through. This makes sense if we think about it. If I try to solve 1 over x equals 0, I'm not going to be able to do that, right? That's not going to work. The way you would solve, or a way to solve that would be to take reciprocals of both sides. But 1 over 0 is, again, undefined. So because that doesn't have any solutions, the range is also everything except for 0 because this is never going to cross through y equals 0. again, if we look at it, we can see the same kind of behavior that, I can see a little gap here and a little gap here. And the further out we go, that's going to sort of continue to be there, right? The gap gets smaller, but it's always there. So again, I see kind of a line that describes what the graph does, right? Looking kind of along a thin strip here. The ends of the function, we spent a lot of time talking about end behavior. The end behavior here is that they're basically flat. And the fact that they're basically flat means that I can imagine a horizontal line that fits in there that shows me what it does. So we get another asymptote, this time a horizontal one. At y equals 0. Okay, horizontal asymptote at y equals 0. And again, the way that you want to think about what that's telling us is that it's describing the end behavior. That horizontal asymptote doesn't give me a good sense of what is happening with this part of the graph, but it does give me a good sense of what happens with that part of the graph, right? What the ends do. The further out I go, the more and more it's going to start to look like that line. Okay, and then the one other thing to maybe notice here, let me just scoot some stuff so I can keep the graph on here. Okay, there we go. Is that if we were looking for intercepts, either x-intercepts or a y-intercept, well, intercepts come from letting something be 0, right? To find x-intercepts, you let y be 0. If I let y be 0, though, I'm setting this equal to 0, and like we just looked at, that never happens, right? 0 is not part of the range, so that means there are no x-intercepts. On the other hand, a y-intercept means letting x be 0, and if I try to plug 0 into this, I get a thing that, again, is undefined, which is why the domain looked like it did, which is why we had a vertical asymptote at x equals 0, which means that in this case, there's also no y-intercept. This does not mean that there will never be x or y-intercepts for rational functions. We'll talk about all this some more. We'll need to look at several examples to kind of get a feel for what can change and how these things work and how it all fits together. But now we at least know kind of what the words mean, right? The terminology and what to expect. And these are kind of the things that we're going to check for, right? Domain, vertical asymptotes or other discontinuities, more on what that means later, horizontal asymptotes, and finding intercepts. Okay, so that's the big idea for rational functions. We'll spend more time on the details in class, but that should give us a start. So thank you for watching and I hope you have a good day.